Welcome back to engineering mechanics. We are continuing with the support reactions. We discussed what is UDL, how to do with uniformly distributed loads. Now we will be discussing how to do it with a UVL, that is, this is called UVL, what is uniformly varying load, and also when there is a couple acting on the beam, how do we solve this? So I'm just clubbing it both in single problem. So two things you should know how to do the UVL. First, consider the UVL. Uniformly varying load, UVL. Earlier was UDL, that is uniformly distributed. This is uniformly varying. So when you have a uniformly varying load acting at a section, so let's draw a uniformly varying load. So uniformly varying load is just like a triangle that is having a load that is starting from 0 to a maximum value at a section. So if you have given this one as a uniformly varying load will be shown like this only. That means a triangle like this. Okay, so and if this triangle has, let's say, length x meters and the maximum what you call the load is given as W kilonewton or Newton per meter, you should know that here the load is actually 0 and it is increasing gradually to W kilonewton at this point. This is the maximum load and this is the 0 load. Actually you should know that this is 0 kilonewton and that is W kilonewton meter, but we will not write it as 0, we will just know it. So if you have a section like this, then this can be converted into a point load by taking into the area of the triangle. So first of all, you should know where the point load is located. In UDL, it is always at the center or the middle point. But in UVL, it is always at a point which is, this is a point load, and this will always be 1/3 of the total length from the largest load section, and it will be from 2/3 of the of section from the 0 load condition. So if I just name it as C and D, so C, D, okay, or just for the ease of understanding, A and B. So from B, which is having the maximum load condition of the uniformly varying load, that is W, that is having the maximum height, and here it is 0. So it will be from 1/3 from the B and 2/3 from the 0 load. And what will be the point load? Point load will be the area of this triangle. You know, area of the triangle is half BH. Area of the triangle is equal to half times base times height. So what is the base here? Base is actually x meters and the maximum height is W Newton per meter or kilonewton per meter. So that will be basically x times W, or basically you can write W x by 2 as the point load value. That is area of the triangle. So that point load will be acting to 1/3 from the B and 2/3 from the A. This is in the case of uniformly varying load. Now coming to the couple of the figure. So again, the theory behind couple is very easy. If you have a couple acting at any location in a beam, let's say that couple is having like this. In our case it is, okay, let's take the same example. So the couple is acting like this. Okay, and this couple is having some kind of forces. Here in question it is given as 2 kilonewton. So for the time being I will just take it as W kilonewton for the generalizing the equation. And you see the couple is given 1 meter on top of the beam and 1 meter below the beam. So if again I write it as x meters on top and x meters on bottom, and this is the point, let's say C. So you know, couple is basically giving a rotation to the beam in this direction because it is pushing the beam in this direction, and two equal and opposite forces separated by a distance is called a couple, and this is the couple center where the beam is attached, and it will be giving a rotation in the clockwise direction to the beam. So instead of writing that couple, you can convert that couple into a moment acting at that location in a clockwise direction, and the moment of that couple will be W times the total distance, that is x, and x multiplies to give you 2x. So that will be the Newton, kilonewton meter will be the couple. So you can convert a couple into a moment acting on the location with taking in the moment of the couple, that is W times the, or the force times the distance separating that. So that is 2x, x on top and x on bottom. So the total force, total moment acting on it will be W times 2x. So now coming back to the problem, we know how to convert both of them, uniformly varying load as well as couple, to a point load and a moment. So if I am considering this as simply supported beam without any, okay, let's consider for the ease of understanding, let's make it as rollers. So you only have to worry about one load acting there. So one reaction acting there. So you have a reaction acting both of them upwards. This is RA, this is RB, and this point load we converted, you see here, it is from 2 by 3 from this position, A to B, A to this point will be 2 by 3, and this one will be this. So if I mark this section as C and this as D, so from C, which is having the maximum load, it will be 2/3 of the total length. So the distance is not given in this question. So let's make this as 3 meters. So if that is a 3 meter distance, so this will be acting at 2 meters and this will be 1 meter. And your point load will be exactly half of the base, that is 1 by 2 times 3 times 6, that is 1/2 times base times height, that is 1 by 2 times 6, that will be basically 3 kilonewton. So you have a condition where your point load is 3 kilonewton acting downwards here, and you already have a couple at here, and you know that couple is rotating and making a couple moment, that is 2 times 2, that is 4 kilonewton meter couple. And you can solve this rest as a simple problem. So taking delta F y is equal to 0, both of them are going up, RA plus RB, and the point load of the uniformly varying load is acting down, minus 3 is equal to 0. Or you can write RA plus RB equal to 3. Now taking Fx is equal to 0, there is no load acting on the horizontal direction because we took both of them as rollers, so that is there is no force. So now taking moment about A is equal to 0. So now you see, consider the moment. RA does not have a moment. 3 kilonewton has a moment. Uniformly varying load acts at a 2 by 3 distance from the A, smallest one. 2 by 3 of 3 is 2. So 3 kilonewton, and it is making a clockwise rotation like this. So that is making a clockwise rotation with respect to A. This is our A. So 3 kilonewton, negative 3 kilonewton times the distance 2 from the A. Now the next point is 4 kilonewton, that is also causing a distance counterclockwise, clockwise rotation, and because it is already a moment, you don't have to multiply with the distance, so that is minus 4 kilonewton meter, and there is an RB which is making counterclockwise rotation about A, and it is at a distance, so total distance is not given, so let's consider from C to D as 5 meters, and from here it is 3 meters. We already took 3 meters here, so the rest of that is 5 meters, so plus RB into 3 plus 5 would be 8. RB is acting 5 plus 3, 8. 8 meters is equal to 0. So if you solve this equation, you will get 8 RB is equal to negative 6 minus 4 will be negative 10, and if you put it in the other side, 10, or RB is equal to 10 over 8, that is basically 5 over 4. 5 over 4 is 1.25 kilonewton. RB you got, RA you can get it from the other equation, so RA is equal to 3 minus RB, so that will be 3 minus 1.25, that will be 1.75. This is how you solve this problem, and there should not be any angle because we took both of them as rollers. If there was a hinged beam, there should be a horizontal force also, then you should do the same principle as we did earlier. So the important thing is you should know how to convert uniformly varying load into a point load, as well as how to convert a couple into a moment acting on the beam. So I hope this is clear. Thank you.